To recap what we stopped at yesterday, so we had a bunch of theorems that helped us generate the phase space Hamiltonian, uh, and from that we had the new equations of motion, which told us how a function evolves, and from that we had the Dirac-Bergmann algorithm because, as I said, a point QP on gamma sub p must remain there at later times. Right now, what we have is just time evolution. Uh, we just have time evolution in these bunch of equations, but we also want them, say, q at a later time and p at a later time, must remain on the constraint surface. Otherwise, otherwise we're going to have some inconsistencies, like assuming we had some momentum and then it evolves and then it's no longer on the uh, gamma sub p. That means we've just lost information about our system, and that's really not physical. And like losing information is always bad. If you are a physicist, you know that.
Yeah.
So we had a bunch of so what we did was we ensured that the constraint phi sub m must evolve just like q and p, so that as q and p evolves, the surface itself like sort of uh, keeps in touch with q and p. So that means phi sub m has to go in the time evolution equation, and then we got the this equation here of with hm and cmn. But again, it's the matrix we care about if we care about uniqueness in solution. So there were cases if it were if the determinant was non-zero, which means that cmn is invertible, then we can just directly solve for un, and then this is what the time evolution looks like, and that's it. That's the end of the story. If determinant of c is zero, then we really can't solve, we can't invert, and we can't solve for un, and then we face with new constraints which are called secondary constraints. Note the difference between the primary constraints that we have. So the primary constraints that we had, this terminology is kind of confusing. It might take time to sort of get used to. Primary constraints we had were because of the Hessian itself, like this eigenvalue eigenvector equation on the Hessian gave us those that independent set of Lagrange constraints, which we can convert instead of the velocity, we can put in the momentum for the momenta that we can solve for, and those are called the primary constraints. On the other hand, the secondary constraints arise from the consistency equations themselves. They have nothing to do directly with the rank of the Hessian. Okay, so we just use them as constraints, apply consistency on them because we all want them to hold as well on a submanifold gamma 1 of gamma sub p. And then again we the matrix we get by the Poisson bracket between uh, phi j and phi n, we can get a matrix cjn, or maybe I should call it prime because it's in the next step. We may get tertiary constraints depending upon the invertibility and the corresponding determinant value. And then again, since we call this an algorithm, it really is an algorithm because you keep repeating until consistency is attained, or that you reach the determinant of c is non-zero condition where you can actually solve for uh, c the inverse, the multipliers. So fine, this is all well and good, but what's the geometric perspective? How do we get intuition about some abstract thing like this? Geometric perspective. So the first point I want to make here is, in general, gamma sub p is not a symplectic manifold. If you think about this, and if you think about what symplectic manifolds mean, there are manifolds like T star n, T star s. So symplectic manifolds are manifold equipped with a symplectic form. So if it's not a symplectic manifold, which means uh, omega, which was the ambient space symplectic form, if you restrict that on gamma sub p, that is not a symplectic form. That's all it means in general. It could be in a special case, but in general, it's not. Uh, First, let's just consider the inclusion map J that takes us from gamma sub p, which was also denoted as the image of the tangent space th under the fiber derivative. It takes that and it sort of places it back into the entire cotangent space T star s. So this is called the inclusion map. Now the two form that we have on gamma sub p, by pulling back symplectic form omega from the whole of gamma, is omega sub p equals j pullback omega. That's just how the pullback works. So this omega sub p, or the symplectic, sorry, the two form on gamma sub p is not symplectic, but it is pre-symplectic. So symplectic form was bilinear and non-degenerate. In the case of a pre-symplectic form, it will be bilinear, but it will be degenerate, which means if you have this map B that takes an element of tangent space to interior product of omega sub p with x, the kernel of this thing of this thing is non-trivial. Why? Because it's degenerate. That's what degeneracy means in this case. And this is partly got to do with how the primary constraints were defined, because if you remember the primary constraint equation, it was some equation involving q's and p's and then set to 0. Well, if you take the gradient of that, you're going to get a term which looks like that, and couple of terms which look like that, give you the directions where the symplectic form is sort of, it can like die away. That's one perspective to think about it. But the point is that you have elements from this non-trivial kernel. So your x can be expressed as some x with elements from the non-trivial kernel under this mapping would produce. So it doesn't matter what we have here, like this always will have uh non-unique values that get mapped to one common thing, which means two distinct values of the tangent space actually get mapped to the same thing. And if you say that, well, in well-behaved manifolds, the dimension of the tangent space and the cotangent space are the same, That means there's a couple more points in the cotangent space that don't have a pre-image in the tangent space. So let me just write this observation. So couple of points in, sorry, cotangent space don't have pre-image in tangent space. What that means was, remember when we had a symplectic, normal symplectic form, we could just convert a vector into its dual. We could transform it using this operation, this interior product operation, and then this was a one form, for example, or an element of the cotangent space. Now we can't do this anymore because, or at least we can't do this uniquely because, at least we can't reverse this operation, because what's going to happen is, as I said, there's going to be some elements in the cotangent space, say df is a one form, that will not have any dual in the tangent space. So no dual in the tangent space. So we really need to separately talk about the range of this map of B. We really need to talk about the range of B, because the range of B determines what one forms actually have corresponding uh, vector elements. So that's the entire idea that I'm gonna sort of build upon in this geometric perspective. Assume you have HC, constrained Hamiltonian is energy, the Lagrangian version of energy, um, composed with the fiber derivative inverse. So what the equations we want to solve now through, the Hamilton's, the equations of motion, basically just become where x is the solution that gives the entire motion on the phase space, on gamma sub p rather, is zero. But as I said, this has no unique solution. What I've written here just now is just the symplectic version of Hamilton's equations of motion. Nothing fancy. But this, unfortunately, unlike with the regular non-singular cases, has no unique solution for x belonging to tangent space, because B, as I described before, x taking it to the interior product with omega sub p, is not an isomorphism. Why is it not an isomorphism? Because two different elements get mapped to one thing, because of the kernel's non-triviality. For degenerate, and I'm spelling the degeneracy out because you don't want to take the dualness for granted. You can do it in general relativity. You have uh, a vector, you can convert it to lower indices, upper indices, like there's no problem, because that too was non-degenerate. But now we have the degenerate case. It's pre-symplectic. Okay, so now what we need to do, this is that we want x to like satisfy on gamma sub p. This is being on gamma sub p itself. But will it stay there? What about the time evolution? So for that, what we need to do, if dhc is outside range of B, and this is the we want corresponding elements. So we shouldn't be outside the range of B. If we were outside the range of B, there is really no solution. Because otherwise, because if you're outside the range of B, you really can't find an X that will work, that will sort of have a dual back. So we seek, therefore, points of M1 that form a subset M2, where M1 maybe is gamma sub P, where interior product of X with omega sub P minus DHC restricted on M2 is 0. So this is sort of, requesting that we are in the range of B. Now we want X to be tangent to M2. Because think about it, if M2 is like, let me like draw a really, really childish picture. But if M2 is like this sheet here, and X is say some sort of like, X generates some kind of flow that gives the trajectory. Right now X is in the sheet, so it is basically tangent. But if F were to sort of take off at some angle with respect to sheet, so this is escaping the sheet, then at these times X would no longer be tangent, and then that escapes, then we are escaping the range, and that causes all sorts of problems. As I said before, consistency is all about sort of evolving the sheet just like the trajectory evolves. So we just want X to be tangent. We don't want a case like this where it's sort of escaping. So if we want X to be tangent to M2, say assuming if X hat belongs to the tangent space of M2, TM2, then we need X to be nothing but the push forward of X hat. That means all of X is just coming out of some vectors from the tangent space of M2, which means some vectors which are tangent to M2. If X is purely coming out of something like that, then we can rest our case and there'll be no more problems. And J2 is the inclusion map of M2 to M1. This is a push forward. Let me just spell that out. If the solution X is purely coming out of a tangent, the tangent space of M2, then that means X is purely tangent to M2, but that will not generally be true. So that means we need to put more restrictions on X. We need to demand more out of X. So the first statement that we had on top was existence of solution, or what we want the solution to do. And then the after that we expect some quality from this, we some quality control from the solution. That solution must stay on the manifold which is in the range of B, and all sorts of stuff like that. uh, so what I'm going to do is I'm just going to write a bunch of things here. So arrow J4 M3, if we keep demanding tangency and keep restricting our manifold, we're going to get a change of inclusion maps like this. and then this is M1, which is gamma sub p, and then the original inclusion map, which takes us back to the cotangent space, the entire phase space. So M3, we can correspondingly define, since in general this will not be true, we can then define an M3 of points M of M2 such that DHC of M belongs to the dual of the push forward of the tangent space of M2. So the statement I've written here is basically demanding the tangency condition, if you think about it. Since DH of C was already in like it's in a one form, DH is a one form. We need the push forward, but we also need to apply B on it because DH of C is a one form, and J2 of M2 will be a push forward from the tangent space in M2 to a tangent space in M1. So this will be tangent space of M1, TM1, elements of TM1, and then you dual those. And this is fine because we force that we're in the range of B. We're in the range of B, so there shouldn't be really a problem. Although it'll kind of still be non-unique, but let's not worry about that too much. Uh, okay, and then we keep doing this until we have full tangency. So say M L plus 1, M belongs to ML such that DHC of M belongs to B JL, should be push forward of TML. And this process ends when mk equals mk plus 1, which means you can't sort of restrict or reduce it even more, where all of the solution is tangent to mk for some k. And by extension, because x already satisfies uh, gamma sub p, and what we're doing after like m1 m2 are just subspaces of gamma sub p, by just natural extension it will also satisfy this equation because it satisfied this for uh, gamma sub p. It will also satisfy it for a subset of gamma sub p, also called mk in this case. Okay, so this is where we terminate the algorithm. This is what's geometrically happening. We just have a bunch of restrictions at each step of the way. If this is a little hard to digest at first, so if you don't understand all of it, it's totally fine. You can go through the references or my notes that I'm going to post. Now let's consider the kernel, because that was something that was definitive about omega sub p, was its non-trivial kernel. So the kernel of omega sub p, let me just define it, is elements x of tmk. This is after we've performed the algorithm, so we know what k is now, and we know what mk is. Interior product of omega sub p with x is 0. So such those elements of tmk that shed this omega sub p to 0. But any solution of equations of motion is not unique. Why is that so? Because we can take any x, any solution of EOMs, and add a element of the kernel of omega sub p, which means or a kernel of omega sub p intersection with push forward of jk in tmk. because since x is going to be in TMK, by extension we also need the kernel element to also be one from TMK. Now, as I said, this can be seen as a consequence of primary constraints, because even after performing the entire algorithm, we still end up with a non-uniqueness after, let me say, after the algorithm, so that it's clear. So this means that this non-uniqueness is inherent, and it is inherent because it's because of the primary constraints. Now, I just want to start a little fresh subsection here. I will come back to this point of primary constraints when it's become more relevant. So now, right now, we have phi sub j, Poisson bracket phi sub m. We can have some eigenvectors here for a equals 1 to the dimension of kernel of C, where C was like the matrix of their Poisson brackets, and the dimension of the kernel, or the nullity, is just the m minus the rank of C by the rank nullity theorem. So multipliers have general solution u tilde plus mu a va, where the u tilde is the particular solution and this is the undetermined solution by consistency algorithm. Phi a VAM phi m, a combination of primary constraints weakly commutes with other constraints under Poisson bracket, of course. So that means these guys are complete set of primary constraints. So phi a now here comes the definition that's really important in this section. A function f q comma p is first class if commutator of Poisson bracket of f with phi sub j is weakly 0 for j equals 1 to capital J. Set of first class functions is closed under Poisson bracket. So you can say that they almost form a group. I think they do. I think they completely do form a group. And that means HP phase space Hamiltonian is first class just by the definition and the equations of time evolution that we had in the phase space in the reduced phase space gamma sub p. So this definition is important, and a function that is called second class if it is not first class. So now let's denote with gamma sub a, set small gamma sub a, set of primary and secondary, doesn't matter, first class constraints, basically all first class constraints that we need, and chi sub a, the remaining second class constraints, and second class are such that they don't commute. That means the Poisson bracket of this set with itself, second class set of functions with themselves, is going to be a non-singular matrix, because if it's singular then one of them has to be first class, and that's really not the right idea. So alpha, chi beta is non-singular. And then in the time evolution, you can see chi alpha Hamiltonian plus delta alpha beta u beta is weakly zero. Then delta beta alpha, where the raised indices indicate the inverse, as our convention has been, gives u beta x beta is primary second class, otherwise zero if chi beta is secondary second class. You can check this out with definition. Finally, a general time evolution of some observable f on gamma sub p can be expressed as a bunch of these Poisson brackets. So where phi sub a is the primary first class, should I probably move this a little that way? Yeah, that's better. So that's the general time evolution. This can also be expressed as a Dirac bracket. This is what we call a generalized Dirac bracket. There's lots of brackets in physics. There's the Lie bracket, there's Dirac bracket, a Poisson bracket. So yeah, names are important. However, uh, coming to the point of primary constraints that I made earlier before I started this new section that I made right here, and this observation that we had. Consider f delta t as f naught plus f dot delta t. So f delta t is the value of the observable f at time delta t, which you can expand as f naught time at initial value of f, and f dot times delta t. I'm not expanding to higher order. Let's just keep it here. F naught plus, this will just become the Dirac bracket. So f hp delta t, f naught delta t, just use the definition, plus sum over va, where like the phi a are going to be the primary constraints, delta f dt dt a va minus va prime. So I'm now taking the difference of two such f delta t expansions with differing va, because va was totally arbitrary undetermined constant. So let's just take two different va, and when I subtract one f delta t from the other that have differing vas, the first Poisson bracket with the gamma sub p Hamiltonian just vanishes because that's the same, and we just get this difference of va and va prime. And now we can just redefine everything so that it looks like that, where epsilon sub a is va minus va prime times delta t. If you recall infinitesimal transformations of uh, Hamiltonian or Lagrangian mechanics, this kind of has a similar form. But the fact is, f delta t and f delta t plus delta f delta t represent the same physical state. That's the catch. That's the catch if you have some sort of invariance transformations to your physical laws, commonly seen in gauge theories where you have gauge transformations. So that we can say that first class primary constraints generate gauge transformations. I mean, technically, so do first class secondary constraints, but that's that's a different kind of Hamiltonian expansion where you have to do. So when we took like a generalized phase space Hamiltonian, we were expanding. We had arbitrary multipliers in front of the primary constraints. If you sort of also take up the secondary constraints, which are first class, then you sort of you can write that as a general multiplier, which sometimes that is a better idea, because then you can see all the gauge transformations and these infinitesimal transformations pop up. But if you want to represent the same physical state by this change, like this change that we have here, this small change of epsilon a that we have here, if we want that to not affect our system, which means this thing must go to zero, which means this thing should also vanish. That means we need to choose specific a va value. That thing, if you have a gauge theory, is also obviously called gauge fixing. No two things about that. So geometrically, what gauge fixing means is eradicating the problem of the non-uniqueness of the final solution. So we had the kernel of omega sub p. What you do is you construct a different omega sub p prime, which is made from omega sub p, quotient with the kernel of omega sub p. So then omega sub p prime will be symplectic, because you just gotten rid of the problem in its kernel. You've just gotten rid of the triviality, sorry, the non-triviality of its kernel. So then this quotient manifold that you get is symplectic, and captures true degrees of freedom of a system, kind of like the Ruthian does. It gets rid of those cyclic coordinates and keeps the ones that really matter. It's kind of doing that idea here. So when you gauge fix, you're going to have a gauge fixing constraint, call it G, fancy G sub A, you know, uh, set to 0. And what this gauge fixing does, it the gauge fixing constraint along with your your first class constraints, which I think I call, yeah, I guess small gamma sub A, they form a second class system together. And the advantage of a second class system is the multipliers are well defined. Like if we go back here, the multipliers were well defined. Like this entire table gave us all those multipliers. And then we just get rid of all of this undetermined stuff here, and we can just end up in a form like that. So that's what gauge fixing does. You're quotienting that out from your MK, or the manifold you end up with. Okay, so I think that this is all the theory we have. It's time to do some examples. Okay, so examples. So consider the Lagrangian function of q1, q2. So it basically has these two canonical variables, q1 and q2. So it's 1/2 q1 dot squared plus q2 q1 dot 1 minus alpha q1 q2 dot plus beta over 2 q1 minus q2 square. So if you calculate the Hessian, which I will just quickly do here, 10010 is the Hessian, and you can easily see that the determinant of this 2 by 2 matrix is indeed 0. So it is singular. Pi can be found as partial L partial Q1 Q1 dot as Q1 dot plus Q2. P2 can be found as 1 minus alpha Q1. Phi 1, the constraint will then be P2 plus alpha minus 1 Q1 out of the top two equations that we have is weakly 0. Hamiltonian is 1 half P1 minus Q2 square minus beta over 2 Q1 minus Q2 square. And then we have the equations of motion. 0 should be, or this is the consistency equations right here. Plus phi 1, phi 2. This is phi 1. Since we have just that one constraint, we're going to have P1 minus Q2 with alpha minus beta Q1 minus Q2. Because there is no phi 2, the only phi 2 we have is phi 1, so that term just drops. And we end up with this. And now after this, we have a bunch of cases. Case 1, if alpha equals beta equals 0, and the phase space Hamiltonian will look like h plus lambda phi 1. So q1 dot is simply going to be p1 minus q2. q2 dot will be lambda. p1 dot will be lambda. p2 dot will be p1 minus q2. And then q1 will be at plus b for arbitrary functions a and b. Case 2, I urge you to work this out on your own whenever you have time. It's just algebra and like different cases. We have another constraint, phi 2 q1 minus q2 is 0 weakly. Consistency is phi 2 h plus phi 2 phi 1 is weakly 0. That just means we can solve for lambda in this case. P1 minus q2. The phase space Hamiltonian is 1 half P1 minus q2 square plus P1 minus q2 P2 minus q1 minus beta by 2 q1 minus q2 square. Notice that phi 1 and phi 2 Poisson bracket is 1. So it's a second class constraint. And in general, phi A, phi B Poisson bracket is this matrix 0, 1, minus 1, 0. It will be anti-symmetric because the Poisson bracket itself is anti-symmetric. Okay. Which ends up giving us q1 dot p1 minus Q2. Q2 dot is P1 minus Q2. P1 dot is P1 minus Q2. P2 dot is P1 minus Q2. So if alpha is non-zero, we have phi 2, the alpha, P1 minus Q2 minus beta, Q1 minus Q2 is weakly zero. And that just gives us consistency phi 2h plus lambda phi 2 phi 1 is minus beta P1 minus Q2 minus alpha Q1 minus Q2 plus beta minus alpha square. Lambda is weakly zero. Now the second last case, alpha non-zero, but beta is alpha square. What that does is phi 2 then becomes P1 minus Q2 minus alpha Q1 minus Q2 is weakly zero. That just gives minus alpha phi 2 is weakly zero. And the equations of motion then are Q1 dot is P1 minus Q2 plus alpha minus 1 lambda. Q2 dot is lambda. P1 dot is alpha square Q1 minus Q2 minus alpha minus 1 lambda. P2 dot becomes P1 minus Q2 minus alpha square Q1 minus Q2. And then the final case is when alpha is non-zero and beta is also non-alpha square. So lambda can be solved for as beta over beta minus alpha square. P1 minus Q2 minus alpha Q1 minus Q2 minus beta per alpha Q1 minus Q2. And then the equations of motion Q1 P1 minus Q2. Q2 dot is beta over alpha Q1 minus Q2. P1 dot is beta over alpha Q1 minus Q2. And finally, P2 dot is 1 minus alpha over alpha times beta Q1 minus Q2. I didn't want to do all of this algebra. That would be uninspiring. You can, if you want to do it, you can do it on your own, because you know what the Hamiltonian is now. You know what the Lagrangian is now, and then you can check. So I think that's the crux of constraint mechanics. And as you can see, we sort of got a sneak peek into why this is kind of important for gauge theories. And